Hi everyone, thank you for joining the talk. My name is Brian and I'm a statistics and machine learning PhD student here at Imperial College London. I'm working towards this PhD part-time and I'm also working part-time in the industry as a machine learning scientist at ASOS.com. Today, I'd like to share one of my recent work done together with Ben and Emma on how we can quantify both the value and the risk of reducing uncertainty in order to make better decisions. Let's start by talking about uncertainty itself. Uncertainty is everywhere, and perhaps the events in the past year just shows it's prevalent. Now, most of us in our day-to-day decision making, either as an individual or as part of an organization, are trying to reduce uncertainty in a way or another, because that simply makes our life easier. Studies have shown that us humans are better in making good decisions in the face of lower uncertainty level. However, it appears that we are not that good in gauging the level of uncertainty that we should get rid of. Very often you can hear people complaining, well, I spent all the time just now trying to get clarity on X. And turns out at the end, it doesn't really matter. The entire thing isn't worth the effort at all, or these complaints. Now that leads to me thinking, well, what if we can quantify the benefit of reducing uncertainty? What if we can treat the task of reducing uncertainty just like everything we have to juggle from day to day and decide if it's worth it or not? And so what started as a work to value and justify my research interests in experimentation and measurement capabilities on the web industries, for example, like control experiments, econometrics, large-scale causal inference, and so on, has evolved into a very general framework that tries to answer what is the value of being able to reduce measurement uncertainty. In the next 5-6 minutes, I'd like to give an extremely high-level overview on why reducing the level of uncertainty helps us to make better decisions and how we can quantify the benefit. And here we are using example of prioritization. Let's say we just built a new startup. It doesn't really matter what the startup does. All we need to know is that we have 4 available projects to do, but being a startup, our capacity is limited to 2. Now, in an ideal world, we'll have access to an oracle telling us the true value of these projects for whatever notion of value that we care about. So in the illustration, we have on the x-axis with increasing value projects apple, orange, banana, and grapes. Now, a natural thing to do is to rank these projects by their value and pick the top 2 to work on. Now, of course, we don't live in an ideal world. In practice, the set oracle don't exist, hence the opaque icon now on the illustration. What we often do is to estimate the value of these projects and rank according to the estimates. From a statistical perspective, the estimation process is just similar to putting some noise, some uncertainty around the true yet unobserved value. And every time you want to estimate the value of a particular project, you basically just take a random sample from the resultant noise distribution. Now here I use the long horizontal lines to represent the level of uncertainty. Without precise measurement techniques, for example, experimentation and measurement capabilities, what people often do is to try to guesstimate the amount. They do back-of-envelope calculations and so on. However, we all know that these forms of estimations are extremely noisy. And in the presence of such a huge level of uncertainty, low true value projects, for example, Project Apple at the top, may leapfrog others and appear to have a high estimated value. Now, in our prioritization process, where we prioritize by estimated value, we will have chosen Project Apple. But we all know that this is not the optimal choice. This is because we don't really care about the estimated value. What matters to us is the true value. On the other hand, we argue that things like experimentation measurement capabilities will help us to lower the measurement uncertainty when we estimate the value. Now, the question here is not what lowers uncertainty in our value estimates, but the fact that having a lower uncertainty level, here represented by shortened horizontal bars, means that a high true value project, for example, Project Banana, is more likely to be selected by virtue of their own value, their intrinsic value, but not because they get lucky when we estimate their value, as in the case of Project Apple. Now, all of these is known under the topic of ranking under uncertainty. It's not new. For example, people like Zuck et al. Has been talking about this in a conference called Uncertainty in AI back in 2007. While they're interested in how the rankings behave under different uncertainty level, in our work, we are quite interested in communicating the value of reducing uncertainty in terms of the value of the projects themselves. So back to our startup example, the value of having lower uncertainty would then be the difference between the case, the difference between the true value of the projects they have selected under a lower noise, that is Project Grapes and Banana, that and the true value of the projects they've selected under a higher noise, which is Project Grapes and Apple. Now, not all organizations will have 4 projects to work on and the capacity to work on 2. Some organizations might have a worse guesstimating ability to start with, and other organizations might acquire much better measurement capabilities that could help them reduce the level of uncertainty by quite a bit. What we need is actually a general model that is capable of capturing such a wide range of circumstances. So that is what we set out to do in our work. We try to model the true yet unobserved project values, having some sort of average and some sort of spread. And then we add some measurement noise, which again has some others average value and some sort of measurement uncertainty to obtain the estimated yet observable project values. In our prioritization regime, what we will do is that we will pick all the projects, rank them by their estimated value, and choose the top, let's say, M of them to work on. Now here there are 2 challenges. The first one is that after knowing which projects that you have chosen, we need to find out what is the corresponding true values of those projects, because once you start ranking, the indices starts to mess up a bit. Having that addressed, we then ask the key question. If we change the measurement uncertainty, that is the uncertainty level represented by sigma square of epsilon, how would the true values of the project that you're chosen in the prioritization process change? Now, in our work, we are able to calculate not only the expected value of the change, but also the variance of the change, representing the risk of a lowered uncertainty. This allows us to compute something called Sharpe's ratio, which is very common in finance, that allows us to compare the value of decreasing the uncertainty level with other things, other investments that we could engage ourselves in. I think I'm running out of time, so this is probably a fairly good place to stop. If there's one thing that you should take away from this talk, I believe it will be there is indeed a value in reducing uncertainty. And knowing what that value is will help us to make even better decisions. I guess this is perhaps more important in the age where uncertainty is the norm. If you're interested in the work I've just described, the work is published in ICDM 2019 and later extended and put on Data Science and Engineering Journal under the title, What is the Value of Experimentation and Measurement? And the link is available on the top right hand corner. I've also written a Medium blog post, perhaps more gentle, accessible introduction to the topic, which is available on the second link. The code which is used in the experiments that I've run, which I didn't really talk about in the talk, is also available on my GitHub repository. If you have any questions, please do ask during the Q&A session. I'm also happy to answer any questions you might have after this session on Twitter or LinkedIn, and my handle is available on the bottom right-hand corner. So that's it. Thank you for your time. I hope you enjoyed the talk and have a nice rest of the day.